to start. I will start just with like the big thanks ever for you, Kata, but with a little introduction. Okay, so it's a great pleasure to introduce Dr. Katharina Jähn-Rickert to give us our first international lecture of the Stomatology Academic League of the Federal University of Santa Catarina. Katharina Jähn-Rickert is a principal investigator at the Department of Osteology and Biomechanics at the University Medical Center Hamburg-Eppendorf in Germany. Her work focuses on the functional investigation of osteocytes in bone physiology and pathologies. She studied biochemistry in Leipzig, also in Germany, and went to her PhD at Cardiff University in UK, and then also at our research institute at Davos, Switzerland. She also has conducted a postdoc at the University of Missouri, Kansas City in United States. So, Kata, thank you again to agree to talk with us, to share your knowledge. We are just excited to learn here. And so you have like 40 minutes as we agreed, and then some time to questions and answer. I would just shut down my camera just to keep the internet connection as well, but I will stay here all the time. And thank you again. For everyone to know our history, we worked together back in 2016, 2017, when I was at my postdoc in Hamburg, and was really nice. Katharina was one of my supervisors, and I have to say that I learned a lot with her and about a lot of things. So that's why I thought to have this opportunity for also to my students, because it would be really nice if they could learn at least a little bit as I've learned with you. I'm really honored to have you here. So thank you.
Thank you, Gustavo, so much for the nice introduction. Can you hear me well?
Yes, yes.
Yeah, okay, so I will start sharing my screen now. Okay, so thank you for having me. It is also really a pleasure for me to talk about bone quality assessments in this lecture series. And I thought, first of all, let's look at where we are right now, especially with this pandemic that we are currently in. So you see where Hamburg is. And I had to look up where you are exactly. So we are quite far, but still we can have such a lecture together. So it's really great that that's possible. For some of you who may have not heard about Hamburg, so it's a very lively city in the north of Germany. I hope you can see also my pointer here. We have a huge harbor where container ships from all over the world enter. We have a nice opera and concert house, the Elbphilharmonie. This is our town hall in the center of the city where all the shopping streets are. We also have some parks, places for green, some relaxation also in the big city. And now I have to say, you probably heard everything about me already because Gustavo made such a nice introduction. So I'm now at the Department of Osteology and Biomechanics in Hamburg, and coming from Germany. I decided to perform my PhD at the AO Institute in Davos in Switzerland. My university was in Cardiff, so in the UK. So I was quite liking the idea of getting into an international research environment, learn different ways of looking at data, but also the different people of how they approach research. So that was really nice for me. And I got the chance to work with Professor Bonewald in Kansas City when she was there at the time for a postdoctoral fellowship. Then I already came back to Hamburg because I did miss my home country, and went back for a short-term visit again to the US, and now I'm in Hamburg and super happy to be with Björn Busse, who's my direct supervisor. So I thought we're gonna start with a small introduction to bone matrix and bone cells, so that we are all again on the same page. And then we're gonna talk about bone quality assessments in research. I've picked a few of them: microcomputed tomography, histology, electron microscopy, also confocal microscopy, and we're gonna also touch a little bit about FTIR. There are more methods, but I think with those one, I feel the most comfortable telling you about my impression and what one can do with those. So bone tissue is quite fascinating when you start really getting to know the tissue. It's a dynamically regulated, mineralized connective tissue. And as you can appreciate just by this scheme of the skeleton, bones have such different forms and they fulfill specialized functions. So we have the long bones that are good for the locomotion, that are load-bearing when we are exercising, that are also building up on their mass and strength if, let's say, we are a tennis player or we are running daily or something like that. We also have bones that main function is to protect internal organs like the ribs or also in the skull. Bones and the bone matrix is a storage place for minerals, but also for growth factors, so that can be important at certain times during a life cycle. And the bone marrow is the production place for the red blood cells. So as mentioned already with the long bones, we have a special adaptation mechanism. So to mechanical loading, the bones can adapt their shape and their mass. Also, mineral metabolism is regulated in bones. So if you're thinking about a woman who's lactating, so producing milk for the baby, while calcium is also supplied with, the food that we eat, but also calcium is taken from the bone matrix. So that's an important point. And then also bones are quite astonishing when you think about fracture healing and regeneration. So if you have ever experienced yourself a fracture and if the bones are positioned in a good way again and you are a healthy individual, then there's a great chance that the bone will regenerate itself to its starting point. So that's quite impressive. If you go more into the detail of the bone structure, you can appreciate that it's arranged in a hierarchical structure. So if you have now as an example here this long bone, at the diaphysis you have this spongy type of bone, trabecular bone, that has quite a large surface area there and is also metabolically very active and very highly remodeled. We will talk about this in a few seconds. And the cortical bone, the compact bone that is here along the shaft, is arranged in these osteonal structures, where in the center you have an aversion canal for blood and nerve supply. And around that, in a circular orientation, are the osteocytes arranged within the lamellar structures. And if you go down to the even nanoscale level, the two major components of the bone matrix are the protein type 1 collagen. It's arranged in these lamellar structures, and then incorporated into these are the mineral crystals, hydroxyapatite, so of calcium and phosphate nature. So there are specialized cells within the bone that have the capacity to maintain this bone matrix. So one cell types are the osteoclasts. These specialized cells can form a resorption pit on the bone surface where they release proteases, but also acid into and demineralize the bone matrix, but also digest the protein content. Then we have the osteoblasts that form new bone matrix in the form of a type 1 collagen-rich matrix called osteoid. And some of these osteoblasts can later embed into the bone matrix that they formed and also aid mineralization there. And these ones are then called the osteocytes. So just briefly touching upon the bone-resorbing osteoclasts. So these cells actually form from hematopoietic precursor cells that fuse and then form these multinucleated, really giant cells sitting on the top of the bone surface. You can see that in this histological image there, where these red-stained osteoclasts here sit in a resorption pit, and they are stained for TRAP. This is the tartrate-resistant acid phosphatase, an acidic phosphatase that really helps with protein digestion in this acid environment that the osteoclast has created. The bone-forming osteoblasts not fusing, they are single nucleated, they stem from mesenchymal progenitor cells, and if they are active, they are really cuboidal, as you can see here on those images. These are the little osteoblasts. You are usually finding them in a sort of seam, so they are never really alone. There's always a group of them sitting on the bone surface. They have a small non-mineralized osteoid layer below them, so the freshly secreted type 1 rich collagen matrix that they are producing. And then once they start embedding, as here, then they become these, we say, fully differentiated type of cells, the osteocytes, which have quite different characteristics. So from this background image, you may appreciate the network of the osteocytes. So this was a bone that was infiltrated with a red dye, and you can see here these canals where then the red dye also infiltrated here these osteocyte lacuna. So these are the places where the osteocytes cells sit inside. And these connections here are the canalicular channels where the osteocytes have their dendrites inside. There was quite a nice paper from Natalie Sims in 2015 who estimated the average number of osteocytes in a human skeleton. So she estimated around 42 billion osteocytes with about 89 dendrites per osteocyte, making up an incredible length of total dendrites and a really great number of active surface that the osteocyte has. So while in former times, looking at osteoblasts and osteoclasts, this, so to say, was considered as the bone surface. We should nowadays also not forget that the osteocytes inside their canalicular network also have a surface area where they can work on the bone matrix, and that's quite a huge surface area. So here is a schematic image of such an osteocyte with its cell nucleus sitting inside its lacuna. Here are the dendrites inside these canals. They are called canaliculi. And what do we know for functions of osteocytes? So due to their location, they're inside the mineralized bone matrix. Early on, they were considered as bone's mechanosensory cells, sensing but also transmitting the signals of mechanical loading. We know that they are capable of producing large amounts of rank ligand, the molecule that is able to induce osteoclast formation. In the case of immobilization, for instance, osteocytes can also regulate the activity of osteoblasts via secretion of sclerostin. And then there are even functions of the osteocyte that go beyond the bone matrix. So there are papers showing that they are regulating skeletal muscle functions, but even more distant organs are being regulated by osteocytes. So now let's get back to the topic of our talk. So why should we look at bone quality, and what is bone quality actually? So there was a definition that came up around the time when people were looking at the effects of certain drugs for osteoporosis. So osteoporosis is the age-related bone loss, which is kind of defined as loss of bone matrix and bone mineral density with this disease, and there's a high fracture rate seen in these patients. And as you can appreciate from these images here, so there will be an estimated loads of people in 2050 that will suffer from this disease. It's women and men who will suffer from it, from these fractures that can occur without a great impact, so to say. And bone quality was defined because the researchers found that their normal definition of what a good bone would be like, so to have a bone mineral density within the normal standard deviation rate, they found that, okay, not all of these results that we see can explain the fracture risk that we have determined. So they were wondering what are the other factors contributing to the bone quality and how can they be measured. So what could be the different characteristics to contribute to bone quality and how can they be measured? So here we start with microcomputed tomography. So these are for research lab based so desktop instruments that have an X-ray source and a detector, and in between that you can put your bone specimens like mouse tibia as you see it here, and you can detect, for instance, the microstructure and tissue mineral density. So here with these tibia from the mouse or mice that were in a spaceflight experiment, you can appreciate that the trabecular bone that is seen here and here is much less in the space experiments. So after the mice have been up in space for 4 weeks, one can quantify this, so either by bone volume over tissue volume or also by trabecular number, trabecular thickness, as you can appreciate here below. So this is one way to determine the microstructure. The microstructure of the cortical bone is also possible to quantify here, for instance, at the midshaft of these tibia from the mice. Again, it's the same experiment. So we had mice that were on Earth and also some that went to space. And what one can do is, for instance, as you can appreciate from these images here, determine the cortical thickness, which was significantly reduced if mice were flown to space. But one could also look at the tissue mineral density. So how much of the mineral hydroxyapatite is really within the bone matrix that is there. And what you can see is, even though the difference here might seem small, but it's significantly reduced with the mice in space. One other factor that is not mentioned here could be also cortical porosity. So little pores inside the cortex that have formed due to bone resorption. Microcomputed tomography can also help you to visualize the mineralized bone matrix. So why can this be important? So if you have, for instance, a fracture model like this one that we did in a mouse femur, where we looked at a steel implant over a new magnesium silver implant, and you can see here these implants in the midshaft, in the center of the femora of the mice. And when the fracture was induced, you can also follow then these callus formations here in the general X-ray. But you may appreciate this a little bit better and in 3D micro CT analysis. And then obviously you can turn around your bone and maybe look at the diameter at the midshaft and maybe see how large the callus is. So here with these magnesium implants that are quite special because they can resorb over time, we found that the callus was much larger compared to the steel implants. So microcomputed tomography, of what you have seen before, was the resolution was about 10 micrometer in voxel size. There are also higher resolution instruments, like here work from my colleague Hanyi Hemazian, who likes to look at the osteocyte lacuna. So these are the in the 3D image, the yellow dots, so to say. So therefore she needs a resolution below 1 micrometer. She can also, like in this cortical piece of bone, then see the canal structures in there. So that's quite nice also for imaging, but also for quantification purposes of osteocyte lacuna. So the next point to touch upon would be the histology and histomorphometry, something that I'm actually quite excited about, and it offers so much. It gives you an overview of the matrix and the cells, and you can apply different stainings that might stain a certain part of your matrix in a different color compared to the other one. The stainings also range, so we have the very frequently used toluidine blue, which is just one dye and everything is in a shade of blue, going up to more pentachrome, which uses 5 different staining modalities, and those images are just astonishing. Bone histomorphometry that can be used on histological slides is a way to then detect the bone cell activities in a very standardized fashion. There are international guidelines there from the ASBMR, where one can follow, and the research can be compared in a very good way. So if you look at this toluidine blue stained section, what you can appreciate here is the mineralized bone matrix. Inside of it are the osteocytes sitting in their little lacuna. What you can also see here is this canal structure here, this pore, where on the surface you see a seam of osteoblasts in dark blue, sitting on a lighter blue surface of osteoid, so freshly made bone matrix. And in close proximity are also some bone-resorbing osteoclasts here sitting on their resorption pit. You can also see some of the bone marrow here. Usually what is empty and circular are these fat cells in the bone marrow. There are other stainings and imaging possibilities that one can do. Here actually our work that we did together, Gustavo and I, where we used circular polarized light. So on a specimen that was stained with Sirius red. So you have kind of 2 polarizers, one before and one after the specimen. And if your specimen is birefringent, then the light is kind of scattered and refracted, and you can see the arrangement of certain things. So like, for instance, the collagen fibers, as you can see here down in the bottom. In the cortex, you can nicely see the arrangements of the lamella in this osteoidal structure. So here in the trabecular bone is a nice lamellar arrangement. But then here we were looking at osteophytes, so local bony outgrowths in the osteophyte. The cortex looks not so lamellar and typically formed. Okay, so if we want to detect or measure the bone cell activity, we perform histomorphometry. The cellular histomorphometry can look at osteoclast parameters. So here you can see on the top surface these toluidine blue stained images. We had 3 different groups in the study that we looked at. These were human bone specimens from older individuals that were non-treated for osteoporosis. Then there were ones that were currently getting denosumab drops, so an anti-resorptive. So you can see here the absence of an osteoclast, while with the naive group, there were multinucleated cells on the bone surface. And we had a group where there was the drug was discontinued and osteoclast returned back to the surface. We also looked at TRAP staining, so that was the enzyme that osteoclast used to resorb bone, and you can appreciate these red stained cells on the bone surface. You can then count the osteoclast numbers per bone surface. You can also look at the surface area that they are governing, so that the area that they are really sitting on. And you can also look for the eroded surface. So what is really the ruffled surface where the osteoclasts have been active. Looking at osteoblast parameters, you see in the same groups these cuboidal cells sitting on the bone surface. Below them, this osteoid seam. You also see some of them in the other two groups, and if you then really quantify it, you can detect here quite a difference of the discontinuation group, so an increase of bone formation again for osteoblast number and the surface that they are governing. It's also possible to quantify the surface of the osteoid thickness, and then also translate this into a 3D information of osteoid volume. If your animals, or maybe sometimes also your specimens from humans, have received fluorescent dye labeling, let's say of calcine or alizarin red, one can also perform what is called dynamic histomorphometry. So therefore, two different dyes should be given with a certain time difference. So during bone formation, let's say here the calcine green is incorporated into the newly formed bone matrix, and then if you give it after 5 days later, you can appreciate the amount of bone that was formed during these 5 days. So we did this here in this fracture model that I've mentioned before, and we wanted to kind of see or look at the bone formation within the fracture colors, or the formation of the fracture colors. We had our groups again of a steel implant and magnesium implant, where we looked at the cortical bone here, the fracture colors, but also the trabecular bone, which is seen in the lower part. And one can look for the mineral acquisition rate, so really how many micrometers of bone are made per day. And this can be also translated into what we call the bone formation rate. So nowadays, and it's good, there are also osteocyte parameters included in bone histomorphometry. And for instance, you can count the number of lacuna that you see in the bone specimen, and then you can determine the number of empty lacuna that you see here. Here in the group of the denosumab experiment, we found quite some differences upon denosumab treatment that persisted with discontinuation, where there was a larger amount of osteocyte lacuna that were empty in the trabecular bone, but also in the cortical bone of these human bone specimens. There's also wonderful staining that Tamara Elliston has reintroduced into the bone world, the Pluton silver precipitation, and what you see here are again the osteocyte lacuna, where the silver has precipitated on the lacuna surface, and you can also appreciate the canaliculi and the connections here in this human cortical bone specimen. And there you can really get an impression of how the connectivity is. So how many canaliculi are there? Maybe, as you can see here, these areas are not as connected as the ones here. So that's quite a nice staining, and there are good opportunities also to count canalicular connections. Coming now to electron microscopy, something that we looked at quite a lot when I was in the US, where we looked at the effect of lactation on osteocytic bone remodeling. So while you have heard that osteoclasts are the bone resorbing cells, there was some older literature that also indicated that osteocytes inside the lacuna can also resorb matrix, so the perilacunar matrix, and therefore the osteocyte lacuna should be getting bigger. So we looked at mice that were breastfeeding, so lactating, and we found that in the cortical, but also especially in the trabecular bone, these lacuna were enlarging compared to the divergent mice, so that never had hubs before, and one could quantify this with lacuna area. Electron microscopy, if used as a method of quantified backscattered electron imaging, can also determine the calcium content, so like the true and content of calcium within the mineralized bone matrix. And here I would like to show some data from my colleague Eva Maria Wölfel, who just recently looked at type 2 diabetic specimens compared to individuals that were age-matched and didn't suffer from type 2 diabetes. And there, with this disease, actually type 2 diabetes, we also have a high fracture rate that cannot be explained easily by this bone mineral density measurement that I mentioned in the beginning. So then she looked for the calcium content, and what can one see here is if you have the control and the type 2 diabetic specimens, the calcium content is really similar in its distribution frequency at the endocortex, but also on the outside, at the periosteal side. There was a third group that maybe now out of interest I should mention. So she defined actually within the type 2 diabetic patients a subgroup where the patients had a very high porosity. So you see that also here. And those had a lower average mineralization profile. You can also appreciate that here there are certain parameters that one can look at. The calcium low was higher, meaning that there are more lower mineralized areas in these specimens. Electron microscopy can also be used to look at mineralized lacuna. So what's that? When you think about a lacuna and an osteocyte sitting inside, there is a certain point that can happen in humans, at least we know, upon or after the death of an osteocyte, some of these lacuna can fully mineralize. You can actually see that the best probably here. So there's no cell inside anymore, and it's filled with a mineral. And we also looked at this with the nosomap specimens and found that here in the cortex there was quite a high number of these mineralized lacuna. Electron microscopy can also be used in secondary mode. And if you have your specimen, so your human specimen, infiltrated with the plastic polymethyl methacrylate that is generally used for histological processing, you can then apply what is called acid etching. So give on the surface of your tissue specimen some phosphoric acid, and you can etch away the bone, and leaving you with the plastic that has infiltrated here the osteocyte lacuna, the canaliculi, also blood vessels. The imaging is quite nice. One can also then start to quantify some of the canalicular connections here. So that's also possible with electron microscopy. It's not trivial with bone to use confocal microscopy, but I think more and more papers are getting out from different groups all around the world, and I think that's why we should also talk about this. So when we looked at the lactating mice, we were curious to know if the mice are using, or if the osteocytes are really using an acidic environment to resorb bone matrix around the osteocyte. And we found out from the literature that the green fluorescent protein, so GFP, is sensitive to an acidic environment. So therefore, fluorescence should be quenched, so lowered. So we had transgenic mice which were expressing GFP under the collagen 3.6 kb promoter. And you can see here in the virgin mice, the bone matrix is nicely green and fluorescence. And with lactation, this fluorescence was quenched. You can also not just use transgenic mice, but you could try labeling and then image your fluorescent dyes within the bone matrix. So here we also looked for the acidification again in the same experiment, and we injected the mice with acridine orange, which in a neutral pH fluorescence green. And here you can see it infiltrated the osteocyte lacuna, both in the virgin and the lactating mice. And then only if there's an acidic environment, this should turn red. And we saw when we quantified this that with the lactating mice, there was much more of this acidic form here in the graph seen compared to the virgin situation, suggesting that there was an acidification happening in the osteocyte lacuna. And here I would like to show you also some work that we are doing with cancer models, where we are infiltrating our bone with another dye called rhodamine 6G. This is work from Roschka et al., which I've started to use this method. And then if you're doing confocal microscopy and you're really scanning in 3D into your tissue specimen, you can appreciate here the osteocytes within the bone matrix, also the way the blood vessels in here is connected to the bone matrix. You can even see the cells inside the bone marrow here. And in a close-up, this can be quite appreciated. But lastly, but not least, I would like to also mention Fourier-transformed infrared spectroscopy, because this is particularly interesting if you are looking at the quality of the collagen inside the bone matrix. So here again, the study from my colleague Eva, who looked at these specimens from patients with type 2 diabetes. So as I mentioned before, we had control specimens, then we had the group of type 2 diabetes, and then the ones type 2 diabetic patients that showed a higher cortical porosity. And then she quantified with this spectroscopy certain parameters. There are certain, it's a spectroscopy, so there are certain peaks that one can look at that can give you an information about the matrix. So there's one that kind of shows you what the mineral to matrix ratio is, so how much mineral you have, relatively speaking, in your specimen. So you see here in the periosteal side that the type 2 diabetic specimens had quite a higher mineral to matrix ratio compared to the other groups. There's also a way to look at the maturity of the matrix. So what's if the hydroxyapatite crystal is really mature already, and what one could see that both at the endocortical but also at the periosteal side, the high porosity group had a lower maturity, so speaking for a younger, more remodeled bone, which makes sense with the high porosity. And what is really interesting, and one of the bone quality factors that could become more and more important, are these non-enzymatic crosslinks that one can determine also with FTIR as a crosslink ratio here. And she found that these were at least slightly upregulated with the high porosity, indicating that the collagen becomes more stiffer due to these crosslink, and therefore could change their behavior, potentially affecting upon fracture risk. And this is really exciting. So what have we learned about methods to determine bone quality? So there are quite a multitude of parameters that could be determined, and definitely it makes sense for the individual research project, the bone pathology that you are looking at, to come up beforehand with obviously what's your hypothesis and which one to look at. There are also ones that I haven't mentioned here in these talks, so microcracks and how these propagate inside the bone matrix is very interesting. Mechanical loading experiment makes sense, for instance, in animal models where you perform maybe 3-point bending, but also this can be done on bone biopsies with indentation experiments where you can get an information about mechanical properties of your specimen. Synchrotron radiation-based imaging can be quite a way that also some people in our group are looking at to see how the mineral crystals are orientated, what size they have. And what one should also not forget are the serum parameters. So to look for molecules that are released upon bone resorption or bone formation, and thereby determine what's going on with your bone pathology. So thank you very much for your attention. This is an older picture of our group. You can probably also see Gustavo in here. And this is Björn, the head of the group. And thank you again. And now I would like to take questions.
Thank you for the amazing. I'm really stunned because you know, you know how much I love this subject, and I was just having a lot of ideas here. We have here watching us master students, PhD students, but also students that are just starting, and was really nice that they are just keeping this, because they could start to think what they want to research in the future. So thank you, my friend. It was amazing as always. And just give me a few seconds. I will say something in Português. Pessoal que está assistindo no canal do YouTube, podem, né, fazer as questões. A gente vai conversar um pouquinho aqui com a palestrante. Então vocês podem enviar para nós aqui. A gente conversa um pouco. A gente sabe que é um tema um pouco mais complicado, mas o interessante é que vai ficar salvo, depois a gente vai ter que colocar as legendas em português, e aí para entendimento exatamente isso, que é essa ciência, e mostra que é possível. Então, quem quer trabalhar a qualidade óssea já pode começar o vídeo às 3 vezes, é o que eu vou fazer. And yes, I was telling them it's important that the lecture will stay at the channel, so they could watch it more and to work on their idea. One thing during the lecture that I was thinking was we need to break a just static tissue. It's not like that. It's super. We need to know more about our and start to talk about just students. They will be working years, probably. Also, the biomarkers on the osteocyte are reliable and more on their practice in hours, for example.
What I have one really for some FTEs, so factor 23 released in large amounts of so there's a way to assess in the serum something where also play a role in a different tissue actually.
In out of the osteogenesis was this idea. So we're trying or maybe the collagen. That different people, and you look together. They I don't know this, but they also prepared to new formation.
Yeah, so the thinner, so to fix something there becomes really challenging. And cement solutions are, so to cement something could be something that one could do. And imaging of a fracture callus, so normally X-rays are used. This could be in 2D, but also CT, so based methods, so where there's a 3D reconstruction possible done, but one should not forget that with these methodologies, one can only see the mineralized bone matrix really good, and the soft tissue callus that actually forms beforehand cannot really easily be visualized. So I mean, with an MRI, sure, one could see that, but I think on average, that's not done.
Yeah. The MRI, we don't have like a lot, and the accessibility it's difficult. But it was like a good question. Isabella asks more about the osteoblasts. So right now, more in the bone cells, and like independent of the disease, but the stimulus for osteoblasts to make new bone. So they came from osteocytes, but others stimulus. What you could say?
Yeah. So actually, what is mostly discussed for osteocytes regulating osteoblast is actually the negative regulator. So because sclerostin has made such a big has made such a big important role in bone homeostasis, but actually it does inhibit osteoblast and osteoblast bone formation. So that's something to stop them. So osteocytes become positive and secrete large amounts of this sclerostin upon immobilization, for instance, and actually stop them. But osteocytes are also a large source of Wnt ligands, and especially Wnt1 has been introduced. So I mean, they are not. Okay, let's not go too far, but Wnt secreted from osteocytes can also stimulate osteoblasts, and within their cellular machinery, osteoblasts have the LRP5, LRP6, and the frizzled receptor, so they are capable of translating the Wnt signal, if you're talking about a canonical pathway, and then actually start bone formation thereby. There are lots of signaling molecules that osteoblasts can actually perceive. So there's also a way, because the bone remodeling is coordinated also in a coupled fashion in a normal adult, by which osteoclasts can signal to osteoblasts. And under pathologies, let's speak about cancer cells, so bone metastases that are sitting inside the bone marrow. Even those cells can stimulate osteoblasts to make bone and like for instance, sclerotic phenotype in these.
Yeah, well, that was my next question was about this. Right now, the samples that I will scan with you guys in January, it's just like this. We collect the samples just next some tumor, or not just tumor, but the lesions from different natures, like cystic nature, or reactive, or neoplastic, and then we would just collect like the bone, like 5 millimeters from the bone lesion interface, and we will we will about to check about this, what is happening there, because if one if you are like just next neoplastic nature, like a malign cancer, for example, or a a benign lesion, but with more aggressive behavior. When they're just invading through the bone, we think that the neighboring bone answers in a different aspects as a cystic lesion, for example. So we aim to understand this microenvironment around lesions. We have to keep like in the lesions in the jaws, because it's in our field. Huh? But I think we will have like amazing results. First, we will have the scans, and then one of the master thesis of Michel, he's also hearing us. It will be to try to identify sclerostin on these samples as well, and
So it really depends on the tumor cells, and sometimes also, also not just the nature, but really also the local cells. So there can be factors from the tumor cells secreted that really simulate factors normally secreted in bone. So sclerostin could be one, but also Wnt can be expressed by tumor cells and act on osteoblasts. But they also can use other factors. So like PTHRP is also something that is commonly been talked about, that can be released by certain tumor cells and stimulate osteoblasts and bone formation.
We want to go for more like to check more proteins, but funding resources are not like the best in the moment. But we will keep on trying. And one of the things that was amazing right now, I have some samples in this patient. So with oral cancer, so we divided the two groups. One with like bone invasion, and another one not having like the invasion, you know, the tumor is nearby, but not just invade the bone. And then we have like different patterns of invasion. Even in one side, like you have more infiltrating, or you just have a lot of osteoclasts working like in line, like just resorbing, so the tumor gets more space and grows, you know. So we will have to think how we are going to study this. We have the samples right now, and I think the first step will be the micro CT, so we can understand the architecture. But then about bone cells and some stomorphometric parameters, you will have to help us a little bit, so to choose how we are going to choose and the best way to do.
Especially with cancers in the bone microenvironment, one thing that we shouldn't forget, so this function of being a storage place, right? So as cancer cells like to, you know, grow more and more and get bigger and get nutrients. So one way is to have blood vessels invading the pre-metastatic niche, and then also, you know, kind of larger formations of those, but also to make the osteoclasts resorb or release all these growth factors that are stored in there, and that can really help and stimulate their growth.
Yeah. So thank you again, my friend. I guess the last question will be not just related exactly. I would like you send a message to you have this career, like, you know, start in Germany and then you were in UK, in Switzerland, US, and you know how some tips and to everyone here, because I guess it's one of the dreams of all, you know, to go abroad and to try life as a researcher maybe. So some advices would be nice.
So, I think there are several ways to go about your career in research, in, you know, the university, or also it can make nice careers and do research. But I can say about my one, and my one is definitely about passion. So I just found out that during my studies that I'm really passionate about doing experiments myself, and I like to find out something that nobody has looked at before, something new, maybe something very easily, like a puzzle where you then think about and try to pieces that put together. So that was the initial passion. And then for me, it was a topic that I can really invest myself in. So something that I find maybe is not investigated, should be, that was the osteo side, and something where I say, oh, but one should really do more with it, to do your experiments and with the people that you have, your supervisors, but also the other PhD students or whoever is there, to really to go on with what you can do in this field. And then it's a matter of I don't know, faith, luck, and obviously at one point or the other you need more funding. You might need to find a better position, and that's why I say maybe there are different ways of doing this. I think you can learn from your, I would call it the peers or your supervisors, or maybe how to write grants, and go from there. But I think also that you should how to say, you should really say what you are working on, what you are passionate about, because that can really inspire other people and maybe wanting them to hire you or to help you by teaching you maybe where to apply for with your grant, or maybe a trick with the grant or something like this. And then at one point comes the life-work balance, and I'm still working on that. Yeah, good. Good luck.
I have to agree, and it's like, and it's about passion, and it's about also lucky sometimes, be in the right place also. I know you said a lot of things. I know for me, for example, as well, I love research, and I was in the same way as you. I was in love to do some experiments, and I decided to be a scientist or a professor or something like that. I was in love to be. That's why I keep on going. Like yes. One last thing. One of the students wants to, say a few words for you. Isabella, you can turn on your camera, please.
Trying.
And a few seconds more things Portuguese. Para todos os alunos também, nós temos aí uma parceria com o departamento, né? E o pessoal da empresa FGM disponibilizou, né, para as ligas acadêmicas. Então, agora a palestra, quem quiser participar quem participou, né, dos sorteios, continuem live aí para a gente poder, as meninas vão poder sortear os brindes para vocês. Tá certo? Depois a live vai ficar salva e meninas podem falar.
Hi, Dr. Katharina. It's a pleasure. We would like to thank you in the name of all the students here. We learned so much with your class.
Thank you. So nice. Thank you. It was also a great pleasure for me. So first of all, I like to how to say, that's also a passion, to give the knowledge that you have obtained onto someone else, a student, a colleague, a friend, and then it's a pleasure to be together with Gustavo.
So thank you a lot. Okay. And yes, thank you a lot. I will see you in January. I hope to not to be like that really cold weather, I always go Thank you, my friend. And I really appreciate the opportunity to learn more and more. And I think I will watch this again like a few times, because I always learn with you and with Bjorn and with the whole team at UKE. And you know, I'm really happy to see a lot of my students here. They just really want to learn more, and I know a lot of them just not will keep on going like in the industry field or something like that, but I know at least a few want to go in science. And I'm seeing some faces here that just start to work with bone as well. Julia, she was at the lab of Pascal Chavassier in Lyon. Yes, she was there with them. And Monique is also working with bone and with bisphosphonates. And so it is really new, and thank you again.
I would like to say thank you, as my friends just say that the experience they had in Lyon, it was awesome. So it's really we have a huge lack of options in the science studying and laboratories and stuff. So that's awesome, and it was a great time having you here, for our students and for our professors here. So thank you once more.
Thank you.
So thank you, Kata. Bye. Ciao.
Ciao.
E agora as meninas vamos continuar, né, com o sorteio.